The mission plan. This is actually header number 3 in the report, but it's actually the first thing you need to do from a technical decision-making point of view, because you must develop a mission plan prior to designing the system and the UAVs themselves. So you do this in this order, but you present it in your report in the same order as the rubric after the system's design. And most of the decisions you make here in mission plan will have the most effect on the objective function. So if we look at the mission plan, some of the design decisions we have to make. We have to choose our sensors, the type of sensor and the number of sensors. We look at our search patterns. We look at the number of UAVs. Remember from the original challenge, it's a system that can be made up of multiple UAVs. The detection method versus confirmation method. The design mission profile. And finally, the ground station selection. The key thing here is the sensors are the main tool to find the lost scout. The UAV is simply carrying them around. So the sensor is the thing in this challenge. So if we look at sensor selection, there are 5 different sensors. They call them X1000 through X5000. It roughly goes X1000 being the lowest cost, the lowest power requirements, the lowest weight, but the lowest capability as well. And then X5000 has the highest cost, the highest what we call slew rate, its ability to move and zoom in on a target. It has excellent zoom, but it's heavy. It's the largest one. It has the highest power draw. So you have a lot of decisions to make here in terms of what sensor or sensors you want to use on your UAV. One thing we need to remember is as we get heavier in our sensors, we'll have less time aloft, that 55-pound limit. And low-end sensors are a good place to start to get lower weight, lower cost, and more time aloft in your first cut at designing your UAVs. So in our sensor selection, some of our experts that we've had working with us on this, we put together some spreadsheets that will be available on our wiki site. We'll talk about the wiki site toward the end, where we looked at the various sensors, looked at the field of view of the sensors in terms of what you could see on the ground, and looked at what altitude you need to be at. As you fly very low, you can see very clearly on the ground for the sensors. But when you're very low, you can only see a very small spot on the ground. So if we look at sensor X1000, when you fly at 100 feet altitude, you can only see a circle on the ground that's roughly 73 feet in diameter. If you go up to 500 feet in altitude, well, you can see a lot more, almost 182 feet in diameter, or excuse me, 363 feet in diameter. And if you go up to 1,000 feet, 728 feet in diameter. So you can see a lot more of the ground. But over to the right of the table, you see that the resolution, the ability to see objects on the ground goes way down. And what we've done, we've color-coded this. The green area indicates a resolution of better than 20 pixels that you would get on a 4-foot person on the ground, and that gives you the resolution to both detect and confirm that indeed that is the missing Boy Scout. The resolution of 1.0 or better or less means you put at least 4 pixels on the person, and with the automated software that's described in the challenge documents, you can perform detection but not confirmation. And then finally, the red areas on the chart is that because you cannot have the resolution to either detect the scout or to confirm them. So you want to be in the green or yellow areas on this. Now what we see here is that without zoom, only the X1000 sensor, remember this is the smallest, lightest sensor, can do both the detection and the confirmation, but it can do it only at a very low altitude, which will really increase your search time because you're looking at a very small part of the ground. The zoom helps increase the altitude, but when you zoom in, you have a very small field of view. You can only see a very, very small part of the ground. So most sensors, they increase the areas viewed with that if you go to the bigger, heavier sensor, but it reduces your vehicle time aloft due to that 55-pound weight limit again. This is going to be one of those big value judgments for your team. Do you go for the high capability sensor or the low capability sensor, and what altitudes are you going to be at? If we look at search altitude, we've created some charts here and to look at what's the impact of the search altitude on the time to be able to search this almost 13 square miles of area. So if we look at a pixel resolution of 4, that's the minimum you need to be able to actually detect the Boy Scout on the ground at that altitude of 100 feet. Your track, this circular area you're looking at on the ground, is about 68 feet wide, which means you have to fly 982 linear miles, and it takes you 313 passes over this area to cover the whole area, which would take you about 17 hours. If we go up to 500 feet altitude, our track is now 337 feet wide. Now we're only flying 196 linear miles, 63 passes, and 3.4 hours to cover the entire area. So what's the real answer? It's a trade-off of the time to detect versus confirmation of that. The hint we want to give you is start with the mid-range values, a moderate altitude. That 500-foot altitude would be a good starting point, and then work out to the higher and lower values. If you start at one end of the range, your real answer's at the other end of the range. It takes you a long time to get there. So start with mid-range values. That's a good place to begin your analysis and your design. On the search patterns, you have a circular area of 4 miles diameter to search. Some of the options for how you search, the patterns in which you do, and there's a link here we have listed in the charts, is from a search and rescue document that we found online and is available to you. There are 4 basic options: expanding square search, where you start from the center and you're expanding your search square; sector search, where you look in different quadrants of the circle; parallel search; and then finally coordinated creeping line search. And you need to look at that document that we've given you a link to get a lot more information on that. We don't have the time in this video today to talk about that. But some of the things you need to remember in any of the search patterns you come up with. You need to avoid tight turns with your UAV if all possible, because when you do a very tight turn, it's possible to lose control of the vehicle. So you want to make wide sweeping turns. Also, when you make very tight turns, you have to bank the vehicle. So now your cameras aren't pointed at the ground. So you're not seeing the ground, and you're not able to get that Boy Scout. Very wide sweeping turns, you can keep your UAV very level to the ground and keep those cameras looking at the ground, looking for that Boy Scout. If your time aloft on your UAV does not permit search of the entire area, you have to come in and land. Make sure that in your pattern that you pick up where you left off. Avoid unnecessary duplication of looking at the same areas in your next flight. And a key thing, remember, your team is at the center of the search area. You don't have to spend a lot of time searching in the center because you're already there. If the Boy Scout was in the center of the search area, you would have already found him because that's where your team and all your folks are. So just remember that key point. So how many UAVs? This is really a cost versus time decision, because when you add UAVs, you're going to add more equipment, more cost to build those UAVs, more ground stations and crews to operate those UAVs. So what are some of the possible options you have here? You could use one UAV with extensive sensors on it, multiple sensors looking out front, back, side to side, just you can cover a lot of area with one UAV. That's going to be a very large UAV, heavy, its endurance is going to be limited because of our 55-pound limit. 2 UAVs. This allows you to keep one UAV in the air at all time while the other is being refueled and ready to go on the next mission. Just like with the one UAV, this allows you to use one flight crew, one operator at one time, so it keeps those crew costs down, but you always keep a UAV in the air. There's never any downtime. The third option is to use multiple UAVs in the air at the same time. You cover the area much more quickly, but you have to have more operators, you have to have more pilots, more equipment to keep those multiple UAVs in the air at the same time. If you look at the detailed background document that was given to you as part of this, pages 13 through 20 have some excellent examples on this one versus multiple UAVs, and it has very good examples of how that cost goes up on that. So please take a look at that. Again, this is like we said with the sensors, the middle answer may be the best. 2 UAVs, one in the air while one's being refueled on the ground. That might be a great place to start. But again, have a discussions and make some value judgments of where you want to start with your team. So once we have in the air, we got to talk about detection versus confirmation. So the total time is the time to detect the scout and then the time to confirm them. And remember from earlier on in the discussion, you have 4 times you're going to go out to confirm that you found the scout and you failed, and on the 5th time you find them. So your time has to include those 5 times you're going to try to confirm that you indeed found the scout. If you have multiple sensors on your UAV, high altitude, you can use high altitude at a wide angle for detection. Then you can fly in for a lower altitude and a narrow angle view for the confirmation event. This is more weight and less time aloft. One idea that we've talked about is a dedicated confirmation UAV. Have UAVs with your lower cost sensors, wide angle, flying over the site continually so you get coverage, and then when you have a confirmation, one way to do it is to use a totally separate UAV. A UAV is designed only to fly out, look at that spot, confirm if it's the scout or not, and then come back to base. That UAV could be very small, doesn't have to have a lot of endurance because you're not searching the whole area, you're just flying out to a specific point that's been identified. So you can have limited fuel, it's lower weight, lower cost, and you can very quickly confirm what's going on there. But you may have to have another flight crew to do that. That's an option you need to think about. Ground station. For each UAV, you have to have a safety pilot, an operational pilot, and a command data link receiver. So if you have multiple UAVs in the air at the same time, let's say you have 3 in the air, you would have to have 3 safety pilots, 3 operational pilots, and 3 command data links. For each sensor, you have to have a video data link ground receiver. So if you had multiple UAVs in the air with multiple sensors, you have to do it. If you had 3 UAVs, each with 2 sensors, that would be 6 video data link ground receivers that you'd have to have. That's going to add to your cost. You have to have a bigger ground station to hold all that equipment. Now for each complete system, you have a shelter or a trailer. You have a sensor payload workstation computer, and that computer can handle up to 4 mission payloads. So if you have 5 sensors flying at any one time, you need to have another workstation computer. And all this is defined by your decisions you made earlier in your mission in terms of the number of UAVs, the number of UAVs aloft at any one time, and the number of sensors. So this just falls out from those earlier decisions that you've made. So when we get to the end of the mission planning part, the decisions you've made so far is you've chosen your sensor type and the number of sensors on each vehicle. You've looked at your search pattern. You've decided how many UAVs you're going to have total and how many are going to fly at any one time. You've come up with how you're going to detect versus confirm that you found the scout. And there's multiple ways of doing that in terms of using your UAVs or a dedicated UAV. And then you've determined what has to be in your ground station to be able to operate these. So you've made a lot of decisions at this point, and most of these decisions are the ones that really have the most impact on your objective function.